All right, so the schedule is just what we've been talking about. We've been mentioning it every day. It's all up there. What we're finishing up is this chapter on amines, because amines are important functional groups. Okay, let's quiet down. They're common in biology and biochemistry. There's amino acids. Nucleic acids have amines in them. So they're very common, and so it's good for us to know something about them. All right, so we started out yesterday on amines, and we talked some about their structure and bonding, right? Their hybridization, their shape. We talked about how to name amines, and we went over some physical properties. We kind of quickly went over, kind of the trend in boiling points, melting points, and solubility. And then we also looked at some spectroscopic methods, right? So we looked at a mass spec, IRs, NMR, and some characteristic things there. So what we're going to do today is that we are going to look at some ways to prepare amines, so how to synthesize them. Some of these methods we know already. A couple of them will be new for us. And then we'll talk about some acid-base chemistry. One of the primary functions of amines is that they are really the most common and strongest organic bases. And after that, we probably won't get there today, but then we do have mostly one more type of reaction, and this has to do with some reactions of anilines. Okay, so this is going to take us back to all of the aromatic chemistry and the chemistry of benzene that we learned before. So it's partly good that we come back to this, because then we can kind of review a little bit of that for the final as well. All right, so that's where we're headed. I don't have a clicker today, so let's to synthesize. Okay, so these are some methods we've already seen before, right? And these are all kind of reductive methods. So we can reduce any of these three functional groups to make amines, all right? So we can start with a nitro group, so we know how to put a nitro group on a benzene ring, and we had various reagents that we could use to reduce this. And when we reduce that, we get an aniline species. All right? The reagents that we learned, we can just use hydrogenation conditions with H2 palladium on carbon. But there were some metals that can be used too. So tin in hydrochloric acid works, or iron works for that as well. Okay, if we use any of those methods with hydrochloric acid, then formally we would get an ammonium ion, or the conjugate acid of aniline as the product, and then how would we get the neutral aniline back? We just treat it with some base. Okay? We can just do that in a separatory funnel if we wanted to. Yeah? I don't know. Zinc wasn't listed as one for this, so I'm not sure. It may, but... All right, so we can make it from nitro groups. We can make amines from amides, right? This is an amide here. And remember, if we reduce an amide with lithium, aluminum, aluminum, there's an L in there, aluminum hydride followed by water. This was kind of an unusual reduction, different than, say, for esters. Remember, it cleaves the bond in the middle, but for amides, it just gets rid of the carbonyl and makes an amine. So if we start with a secondary amide, this is a secondary amide because the nitrogen has 2 carbons attached, we get a secondary amine. All right, if we had a primary amide, so it had an NH2 on the end of the amide without that ethyl group, we'd get a primary amine. Right? If we have a tertiary amide, we get a tertiary amine. Okay, so we always lose the oxygen essentially as a water molecule. All right, we can also reduce nitriles, this is a nitrile, with lithium aluminum hydride. Lithium aluminum hydride followed by water, and this also gives us an amine. Okay, so these are all ways that we can make amines. Primary amine to a secondary amine, or if we want to start with ammonia and we want to go to a primary amine or something like that, then it would seem like the easiest way would be just to use ammonia or the amine as a nucleophile and just do an SN2 substitution. Okay? And we can show this, right? This can do SN2 substitution like this. We'd come down here, we would get a intermediate that would be the ammonium ion, so the ammonium bromide salt. And then to get to the free amine, it would take another molecule of ammonia to pull off one of these protons to give us this free amine. Okay, so this all looks fine, but can you see any potential problems? Yeah.
The reaction just continues?
Yeah, so the reaction could just happen over again, right? Because we have our primary amine now, still has a non-bonding pair of electrons, and so it could go again, right? To put a methyl group there. It could go again. To give us our tertiary amine, and in fact, it could go again to form the quaternary ammonium ion. Like this. Okay, so it's hard to control how many alkyl groups go on. All right? However, sometimes you can get by if you used really an excess of ammonia rather than an excess of the alkyl halide, then sometimes you can stop here. Okay, but it's, yeah.
Where did those methyls come from?
Oh, dang, they should all be those isobutyl groups. Good point. I was looking at the one below it, maybe. All right, let's redo these. Magic, you know. Okay, so this would add another one of these groups. Here we have 2 isobutyl group, 3 now, and the bottom one would have 4. Like that. Is that better? Okay, so sometimes if we could use excess ammonia, we can get it to go only one time, all right? But it's still not such a great way. If we want the ammonium ion, so for example down below, if we use an excess of the alkyl halide, then it really will always go all the way to the quaternary ammonium ion. Okay? If we used a 1-to-1 ratio on the top one of ammonia to the alkyl halide, we'd probably just get a big mixture of all of these. Right? Some of them would go a second step, some would go the third, some would only go one, and we get a big mixture. So it's kind of not a very good way. So luckily, there's a way to get around this problem. For the discoverer to be able to have the reaction named after them. All right, so this is called the Gabriel synthesis. And what we're going to do is essentially what we would do for this reaction here, which doesn't really work so well. Okay, and what we do is we use a different nitrogen nucleophile that we can convert to the free amine in the end. Okay? And that nucleophile is like this. So it has the nitrogen, but that nitrogen is put into this ring with two carbonyls like this and a benzene ring. So this is the actual nucleophile with a minus charge on the nitrogen. Okay? And of course, the minus charge on that nitrogen is delocalized with both of the oxygens as well. Okay, so this is a reasonably stable anion. We would make that anion just through an acid-base reaction from this compound. Okay, this is called, these are always weird, which is it, amide? Phthalimide. Which comes from, well, we'll get there in a minute. Well, we could do this. So these types of compounds that have esters on here instead of that kind of amide type of thing. These are called, phthalates. These are in fact used as plasticizers, right? And I have this when I was in grad school, so I was trying to isolate compounds from insects. And I can't remember what I actually was trying to do. There were some insects that I think I squished up and soaked them in some solvent and then tried to purify some compound. And I had this compound, you guys have done thin layer chromatography, and I had this nice UV absorbing spot, and I purified it, but I had tiny amounts. And so I signed up for the NMR all night long, and I did these experiments. I spent the whole night on the NMR, and then I figured out what it was, and it was one of these phthalates, and it was a plasticizer. It didn't even come from the insects. It came from like the rubber tubing that I was using or something. So I wasted all night long to identify something that came from the tubing. That was terrible. All right. So this reaction with this nucleophile can just do an SN2 substitution like this. And we get this substituted phthalimide. All right, but notice this. It's called an imide because it's kind of like, we could just think about it as a diamide, right? It looks like an amide on each side. And so we can do a hydrolysis of this. And we could just do, say, a base hydrolysis, hydroxide and water. And just like the base hydrolysis of an amide, we will get out the amine plus, and if it's in base, we'll just get the conjugate bases of these two, carboxylic, this dicarboxylic acid. Like this. So this is the conjugate base to phthalic acid. All right? But the reason why this method works pretty well to get to that amine is because our nucleophile here really can only will add one time. Okay? It does have a non-bonding pair over here, but it just doesn't add again. Okay? Only adds one time. Okay, so it makes it a good to make primary amines from alkyl halides, right? Do you think we could just use any alkyl halide? Or is there any limitation on the alkyl halides that would probably work well?
This is a primary methyl or maybe secondary.
Yeah, because it's an SN2 substitution, so methyl would work, primary would work, maybe secondary, but maybe not. Okay, yeah, question.
What about leaving group ability, since that's a relatively stable electron holder?
Yeah, well, I think as far as the leaving groups, it would just, follow the same trends that we've seen. Iodide would be better than bromide versus chloride. You could use those tosylates or those kind of leaving groups as well. Okay, so this is another way to make amines. Ammonia is the primary amine. Okay, so there's another way that we can make amines as well, and this also relies on the amine being a nucleophile. So remember before we talked about the reaction of amines with ketones or aldehydes, right? And so when we reacted even a primary amine with say this aldehyde in the middle, what kind of a product would we get? Anybody remember that? An imine. Okay, it has a carbon-nitrogen double bond. Okay, so in these steps, what we're going to show is kind of an intermediate that looks like that. It's not going to be fully deprotonated, though, and neutral. So if we went halfway, so what we're going to do is just replace the oxygen with the nitrogen, and we're going to have two bonds. I think we could probably show the neutral one as well. But what we're going to do is we're going to go to this stage, and then we're going to reduce that carbon-nitrogen double bond. Okay, so we're going to add two hydrogens. And so we could use, our book doesn't show it, but the other text that I used to use hydrogen and palladium on carbon. But a real kind of a specialized reagent for reducing carbon-nitrogen double bonds is this borohydride like this, and it has this cyanide on it as well. It's called sodium cyanoborohydride. And I'm not really quite sure. It's always stuck in my mind that this sodium cyanoborohydride is good for reducing carbon-nitrogen bonds, but I'm not sure why adding that cyanide there makes it especially good for carbon-nitrogen double bonds. So it's kind of an empirical thing, if anything, for me. Okay, so we just add a hydride, right? That's all we really need to do here. We're adding a hydride like this, and it goes like this, and we get the amine like this. Okay, so we've just reduced the carbon-oxygen double bond. Okay, if we use a primary amine, we could also go to draw out an intermediate like this. Use our sodium cyanoborohydride, reduces the carbon-nitrogen double bond, and we get the primary, no, not the primary this time. We get a secondary amine, right? Like that. And if we start with a ketone, and if we use a secondary amine, then let's just go straight to the product this time. We would get a tertiary. So if we go from a secondary amine, we get a tertiary amine. If we have a primary amine that we do this reductive amination, we get a secondary amine. So each time we're adding one alkyl group in the process to the nitrogen. Here we start with ammonia, and we get a primary amine as the product. Okay, so we are adding one alkyl group to the nitrogen. Okay? Yeah, question.
Quick question. So the bottom one, would we form the enamine intermediate? Okay. So it would just be like the
So it would, yeah, so we'd still form a similar type of intermediate. I think with the secondary, right, if we did it under the normal ways and we didn't do the reduction, then we would get an enamine, right? But either the enamine or this kind of imine type intermediate gets reduced once we add the sodium cyanoborohydride. Okay? All right, so like I mentioned, really, a lot of times the reasons you want to make amines, or that you use them, or that the roles that they play in biology, is that they function as bases, and conjugate acids function as acids. But we've seen before that amines, in fact, can act as either acids or as bases. All right? So recently, we saw an example of amine as an acid, and we did the reaction between diisopropylamine and butyl lithium. Okay, so what did we get out of this reaction? Okay, so this grabs hold of the proton, and so we get the anion, the conjugate base of this amine. So it has two non-bonding electrons on the nitrogen now, and the lithium counter ion goes along with that. And what's our other byproduct? Just butane, right? So what did we call this, or what's the use of that conjugate base there? What is it? It's not an ylid. Yeah. So this is called lithium diisopropylamide, or LDA. Okay, so this was our very strong bulky base that we used to make those kinetic enolates. All right, we used it to deprotonate the alpha position, and it was good because it was very strong, but it's bulky, so it doesn't act as a nucleophile. Okay? And to do this, the pKa, as I remember, I didn't have a chance to look at this up, but the pKa's of these amines is on the order of about 38. Okay, so it's pretty high, right? And so it takes quite a strong base to deprotonate that, okay, like butyllithium. Okay, the more common role is to see an amine act as a base instead of an acid, right? And so this could go here, pull off this proton, we get the ammonium ion like this, plus chloride. All right, so how do we tell for a reaction like this, acid-base reaction, which direction the equilibrium would lie?
Doesn't this depend on the pKa of that?
It depends upon the pKa of the two acids. Okay, the acid on the left, which this pKa is something very low, like 9 or maybe 7, -7. And the pKa of ammonium ions is more like 10 or 11. So I think this is about 10.8. All right, so which direction would this equilibrium lie? Right, well to the products, right? Because it lies away from the strongest acid. Okay? So this kind of chemistry we've seen a lot. But there's a lot of different types of amines, and so we should have some feeling for, the relative acidities or then the relative basicities of the amines. Oops, that's not what I wanted to do. Okay, so here's a bunch of different types of amines. All right? We start as simple as ammonia. We have a primary amine, we have an aniline, we have pyridine, and we have pyrrole. Okay, so we've got some aromatic amines. We've got some just basic kinds. So really, to determine the basicity, what we oftentimes do is look at the acid, right? Their conjugate acid, and then the strongest acid will have the weakest conjugate base. All right, so let's just draw out the conjugate acids for each of these. Okay, so these are going to be the conjugate acids, and so we're just going to have, I'm going to use blue here. NH4 plus, right? NH3 plus. Here's the conjugate acid of aniline. The conjugate acid of pyridine. This is the pyridinium ion. And the last one is pyrrole, and its conjugate acid is not what you would probably predict. Its conjugate acid looks like this. It actually protonates on the carbon rather than on the nitrogen. All right? So what we want to try to figure out here is, I guess, which, ultimately what we want to do is figure out the order of basicity, okay, of the amines. and we can maybe relate that to the order of acidity of the conjugate acids. Okay? So let's just think about the bases. Basicity. Okay, so which of these do you think might be the strongest bases? We have some kind of different categories of amines here. Okay, well, it turns out that the strongest bases are on the left. Okay, because the electrons are very localized, right? And so they're really there to pick up a proton. And so let's look at this versus the pKa's of the acids. So the pKa of ammonium is 9.3. The pKa of this ethylamine conjugate acid is 10.8. Okay? So which one of those which one at the top, ammonia or ethylamine, which one is a stronger base? The ethylamine one. So this is the strongest base. And this is second. Why would the ethylamine be a stronger base than ammonia? Exactly right. So we've talked about numerous times that alkyl groups act as electron donating groups, right? We've seen that in benzene chemistry, right? Alkyl groups are activating groups. We've seen it as alkyl groups can stabilize carbocations, right? The more substitution that we have around a carbocation, the more stable. And in this case, if we have an alkyl group trying to donate electrons to this nitrogen that has the pair of electrons, it just builds up more electron density on that nitrogen, makes it a better base. Okay? So, if we look at the other three, so why then, let's say, why would aniline be a worse base than ethylamine or ammonia? Because it's resonance stabilized. These electrons here can be delocalized into the benzene ring. Okay? So we can think about the other way. If we look at the conjugate acid here, means it has a much more stable conjugate base, right? Because the electrons are delocalized. All right? And so, in fact, the pKa of the ammonium ion for aniline is 4.6. Okay, so if we compare it to, the ethylamine ammonium ion, it's something like 6 orders of magnitude better acid. All right, now the aromatic ones are a little harder to, I think, to figure out here. Let's just go ahead and put the pKa's up. pKa of the pyridinium ion is 5.3, so it's not quite as good of an acid as the ammonium ion of aniline. But the conjugate acid of pyrrole has a pKa of a 0.4. So that's a much stronger acid, meaning pyrrole is a much weaker base, right? So let's just compare those two first. They're both aromatic amines, all right? So why would the pyrrole conjugate acid, or why would pyrrole be a much weaker base?
It's just because those lone pair of electrons, excuse me, you take out the hydrogen, is in the sp2 orbital.
Well, I think our analysis is a little bit backwards from what we would normally do here. Actually, it's easier to think about it from the base rather than the acid point of view. Yeah.
When we protonate the basic form, we're destroying the aromaticity of the ring.
Exactly right. So when we protonate pyrrole, it's over here on the end, the conjugate base here is no longer aromatic. Right? Because it has that sp3 hybridized center in the ring now. Okay? So by protonating that ring, it loses the aromaticity, and so it really doesn't want to do that very much. Okay? What about for pyridine then? When pyridine gets protonated, is the ring still aromatic? Anybody up in the bleachers? Yes, it's still aromatic. Okay? So this one is still aromatic. So at least we don't have that issue. But another way we can think about it is that pyridine, the nitrogen, well, they're all kind of like this, but compared to these over here, this is sp3 hybridized, right? The nitrogen in pyridine is sp2 hybridized, which makes it more electronegative. And when it gets protonated, we have a plus on a more electronegative atom, which is less favored. Okay? All right, so so in general, the aromatic ones are less basic. The aromatic ones that have the non-bonding electrons like this that don't show a double bond to it already are even less basic, okay, because it breaks up the aromaticity. Okay, so everybody kind of get this trend. Here's a table from the, oh, no, it's not. Oh, we got another one. I might have stuck this in. Do you guys have this slide? No, I got this extra one. I made this slide and then somehow I substituted it out. And so I had to put it back in. Okay, so let's look at anilines like this, and we'll get some substituted anilines. On the left, we have a nitro group. On the right, we have a methoxy group attached. All right, so how will these substituents affect the basicity of these two anilines? Which one would be more basic? Left or right? 50-50 chance. On the left? All right, so what we need to think about here is resonance, right? So let's, here, that's not really in equilibrium. I'm just going to redraw it first with the Lewis structure of the nitro group drawn out. Like this. All right, and let's think about the type of resonance that involves the lone pair of electrons on the nitrogen. Right? So we can move these down this way, and we can move them into the ring. All right, so we could draw a resonance structure like this. Plus has a minus here. Right? We can draw another one like this. Oops. Forgot that. This one over here gives us Just draw it like this. Gives us this one. And then what can happen from here? Electrons continue around the ring. What else? They can be delocalized out onto the nitro group. Right? So these electrons can go down here and out onto this oxygen. And we get, oops, that's an N, O minus with a plus there. We get this resonance here, okay? So the non-bonding electrons on nitrogen can be delocalized to the ring in this one, but it can also be delocalized out onto the nitro group. And we already know from benzene chemistry anyway that this nitro group is a strong electron withdrawing a deactivating group. All right, so is that going to increase the basicity of the aniline having the nitro group, or is it going to decrease the basicity? It's going to decrease it, right? So this one is going to be more basic. This one is going to be less basic, right? For the oxygen, remember that oxygen here is going to tend to donate electrons into the ring, and so it's going to end up pushing electrons towards the nitrogen, which just increases the electron density on the nitrogen, makes it a stronger base. Okay? So this is an electron donating group. All right, in fact, the pKa's of these two, the pKa of paranitroaniline is all the way down at 1.0. Okay, so remember, remember when I put a pKa like this, that it's not the pKa for that compound there, right? This pKa is for the conjugate acid. Okay? So the pKa of the conjugate acid is very low. pKa of the conjugate acid over here is 5.3. Okay, so there's a big difference in the, this is a stronger acid, gives a weaker base, and we have a weaker acid, which would give a stronger base. Okay, let's just reframe. I know even online and stuff, this is something that really bugs me, is oftentimes they'll show bases like this and then just say, oh, the pKa is this, right? But these are the pKa's of the conjugate acids. Okay? And these are the bases there then. All right, everybody follow that? The relative of activating and deactivating groups influence it. So here's the table of quite a few of the groups that we've just looked at. So this is kind of just a summary of what we've already looked at. The one that I didn't show is down here. These aren't really amines, but they included in the amides just because they have a nitrogen on them as well. Like this. So if we protonate an amide, if an amide acts as a base, where does it protonate? On the oxygen, right? So this is what we saw when we saw the carbonyl chemistry. So it protonates on the oxygen, not on the nitrogen like we might expect. Why does it protonate on the oxygen and not the nitrogen? Just joking. Situation's the same as carboxylic acids. Remember, carboxylic acids protonate up on the carbonyl oxygen as well. Right? Does anybody remember the reason for that? Right, because there's resonance. Right? So these electrons can be delocalized between the nitrogen and the oxygen. If we put the proton on the nitrogen there, it would be NH3 with a plus on it, and that would be sp3 hybridized, and it can't participate in resonance. Okay, so it makes it less basic, right? So this acid over here has a very low pKa, right? So amides are less basic than any of these other amines. Okay? So let's take this, all of what we learned, and look at a compound like histamine. All right? Histamine has 3 nitrogens on it, and so let's just predict the relative basicity of the different nitrogens on the molecule. All right? So which would be the most basic? Which one? On the left? Out here? Is that the most basic one? Yes, because we see over here that the normal kind of sp3 hybridized amines are the strongest bases. Okay, so that side chain out there would be the strongest base. All right, and then we have the 2 nitrogens in this. This is this imidazole ring, right? Remember, we used imidazole when we were doing protections with silyl ethers. So histamine has a imidazole ring within the structure. All right? So which of these 2 nitrogens is more basic? The top one, right? Because if it protonates on the top one, then the ring remains aromatic. Okay? And there's resonance that can go around. The bottom one is like pyrrole, and in that case, if you protonate there, or if you protonate on one of the carbons, then you lose aromaticity. Okay? All right, so tomorrow we'll look at some of those reactions of anilines. All right? So I will see you in the morning.